We can assess long-term trends. We can provide input, of course, to atmospheric predictive models. So clearly, space science, space instrumentation, together with models, have been a game changer, because that's the title of the series of talks, game changer in environmental science. Of course, I should also highlight that space observation is not everything, that monitoring from the ground, having a field campaign, in particular from aircraft, for example, having laboratory studies is another very, very important aspect that we should not forget. But of course, since we're talking here with the International Space Science Institute, I want to highlight in particular the space observations. Now, atmospheric chemistry is a field that has evolved dramatically in the last 50 years or so. Of course, we have the fathers of atmospheric chemistry who discovered the first species, like, for example, ozone was discovered in 1839 in Switzerland, in particular in Basel. But of course, there's been a lot of aspects. The field has become relatively interdisciplinary, and we're looking at a number of environmental issues that can go from urban smog to biogeochemical cycle, regional problem, ozone layer, and disaster sometime, extreme event that happen, including then also, we have to add to this list the connection between chemical species and climate. Now, air pollution is a major issue from the health perspective. And it's been there for a long time, and it kills a lot of people every day. And so now we're talking very often about an air pollution pandemic that is occurring in the world. So you can see here an estimate done a few years ago that, for example, the presence of particles in the atmosphere reduces the life expectancy of people on the average by almost 2 years. And this is larger in certain amount, by a large amount in certain regions of the world. Now, many years ago, air pollution was a sign of prosperity or building society. But of course, we are coming back from that idea, and we see a number of negative effects that have occurred as a byproduct or a consequence of industrial development, combustion in particular. The London fog has been kind of a red light, or a point where it was clearly showed that we were facing a major issue associated with the quality of air, and large number of people died, 10,000 perhaps in 1952. This is one example, there have been others. This kind of air pollution was associated with burning coal, releasing SO2 and black carbon that were then, well, at least SO2 converted in particle and affecting the city in a very negative way. Now, today you see still particle pollution in many parts of the world, in particular in Asia. And if you go to Hong Kong today, sometimes you can see that people have been placing pictures of Hong Kong where, you know, they take your picture with the buildings in the back, but it's not the reality. It's based on a picture that shows a better air quality. So it's not happening like that every day, but it is certainly a major problem in Asia, and increasingly now in Africa, not to mention, of course, other places like South America. Now, in addition to the particle pollution, we have also an ozone pollution. And this was, of course, highlighted in particular in the 50s in Los Angeles, because there people were witnessing large pollution events. The source of the pollution was not the combustion of coal, but it was the release of nitrogen oxides and volatile organic compounds, VOCs, and then in the presence of light, the formation of secondary species in the atmosphere, in particular ozone, but also some particles. And so just to make a complicated story very short, a complicated story that is really investigated by laboratory people and by people who do field experiment on processes in the atmosphere. But the presence of NOx, nitrogen oxides, the presence of volatile organic compounds, and the solar radiation lead to the formation of ozone. And ozone, just like particle, have impact on health that can be relatively important. This is an old picture from 1955 showing a policeman, I think, a person on a bicycle, on a motorcycle here with a mask traveling here through city of Los Angeles. We're not in that situation anymore because a lot of progress have been made, but the situation was relatively serious. And if you look at, for example, the impact of particles, both inside the household, which is a very important source of pollution, in particular in developing world, in the low and medium income countries, where cooking is done without any precaution, but also the ambient particulate matter pollution. In other words, outside in the atmosphere, you can see that they count about the largest causes for death. And you see a lot of newspapers saying that air pollution becomes a global killer, more than dirty water, that it kills more people than cholesterol or malaria or AIDS. So you've seen that in the press. And so action is needed to contain this pandemic. And of course, in the long term, we need to mitigate the sources, reduce the sources. We need to introduce new technologies, new way of moving, management of wave, traffic, etc. But in the short term, we need also to be able to forecast air pollution episode so that we can take immediate action to reduce the exposure of people and the related health effect. And that's what I would like to highlight in this presentation, and like to talk about an integrated system for the observation, the analysis, and the forecast of air quality. Here is a kind of a plot that shows how a system would be looking like, something I put together with my colleague from NCAR, Rajesh Kumar. And you see here that essentially to do a chemical weather forecast or an air pollution forecast, which you can do at the global and regional scale, you can also do it at the local scale. You need information, of course, about emissions. It's very important. We don't have always good emission data because it's very difficult to establish. It's related to activity, economics, traffic, etc., and it's changing relatively quickly. But we need also satellite observation, first on the weather, on the meteorology, but also on the atmospheric composition. This has to be complemented by in situ observation that gives you more information about what happens either at the surface or as a vertical profile, which is generally not what the satellites are providing. So knowing the weather or knowing the weather forecast, we can try to forecast air quality in different parts of the world. And then, of course, we do it at different scales. When we have a forecast, we have to evaluate the forecast. We have to evaluate the products we are generating. And finally, we have to disseminate the forecast that we do. And there are now more and more groups, including private companies, who are giving you on your telephone information that is current, but also more and more prediction or forecast of how the air quality will be moving. This is an example here from one of these companies. This is Brisometer. You see on the left, so I picked Switzerland, I picked Bern, where the institute is located. You see at the moment, high pollution in northern Italy, but clean air in Switzerland, and you see excellent air quality today. And you see the evolution for the rest of the day. You find those kind of things now on your phone, but there is a lot of operation that exists before you get to that point. The first one is to get the right emissions that you are going to consider in your forecast. We now have global field of emission. This is coming from a database that is established in Toulouse, Annie, in your institute, called ECAD, that's run by Claire Garnier. And you see here, this is an example of global nitrogen oxide emissions in July 2015. And you see, of course, the hotspots. You see China, you see India, you see Western Europe, Eastern Europe, you see the eastern part of the US, and then you see other regions too. We can look more specifically for Europe, where I am now, and then you see that we have a lot of good spatial information. You see the roads, for example. You see the ship tracks, which are a relatively important source of emissions, and you see the cities that appear here on this graph. Now, the emissions are changing. They change. There are trends in emissions. This is for China, of course. China is a good example. You see the NOx at the top, you see the volatile organic compound at the bottom on the left, and you see that there are differences between the estimate of emissions by the different inventory. Some of the inventories start to see a decrease in the emission, which I think is there now because of the action taken by the Chinese government. Some don't show that yet very clearly. And then here on the right, you see another estimate by the Chinese group in Beijing. Then, after you have identified and established and quantify your emissions, you need to have some view on how you're going to treat the chemical transformation that occur in the atmosphere. And that's a very complicated process. And a lot of work has been done by a number of universities, a number of research centers in the world to try to see how the emitted compounds lead to the formation of secondary species. And among the secondary species is here ozone on the one hand, but you also have the aerosols, and in particular, the secondary organic aerosol, which are produced by, as you can see here, many pathways. It is a very complex problem, and it's a problem that has required generation of scientists working on the different reactions that can occur in the atmosphere and using the measurements that are done, because there is nothing else than measuring the reactions in the atmosphere itself. Now, I'm going to show you just one a bit complicated graph that is called the ECMA diagram that shows you here, these are the ISO line, the amount of ozone that is produced. So high ozone is on the right, on the top, low ozone is here on the left and on the bottom. And you see that those lines are far from being straight lines. The chemistry is not linear. That's what's make it very complicated. And the point on which we operate depends very much on the location. So if we are, for example, in the country, in a rural area with relatively large VOC, mostly produced by biogenic activity, but low NOx because, let's say, little traffic, no factories in the region, we are at this red point. If we want to reduce ozone, we have to go along this line. We have to reduce NOx. So essentially, we are in the regions where ozone production is controlled by NOx. If we want to make the air quality better, we have to attack NOx. We have to reduce NOx. We are in a region called NOx limited. But if we are in an urban area, very often, we might be at this point here where the VOCs are probably not as high in concentration, but we have more NOx in the region. In this case, what happens, if you reduce NOx, you will increase ozone. You will increase ozone, while here you will decrease ozone. And so acting on NOx depends very much, if you want to clean the atmosphere, on the region in which you are. So what you have to do in this case to reduce the level of ozone is to reduce the VOCs. So we will remember that because I'll show you a bit more about that a bit later. So if we want to have a predictive capability, we need, of course, models. I'm going to come to that. We need lab studies, we need in situ observation, we need field campaign, and we need satellite, we need remote sensing. So let's see a bit what we do in terms of satellite observation to better investigate how the atmosphere functions. We have quite a few instruments flying, and different types. Some have a high spatial resolution, some have a less large spatial, I mean, the resolution might be changing, the temporal resolution will be changing. I'm going to deal with two satellites. I'm going to talk about one of them called TROPOMI in a minute. So that's spacecraft gives you information at a frequency of about once a day, but it has a relatively high spatial resolution, under 10 kilometers, which is now the kind of scale that we use to look at air pollution, which is a very urban, very resolved problem. And then you will see now what is, I think, for the field, a new revolution, which are geostationary satellites. And I'll talk about that in a minute. But here we have about the same spatial resolution, but we start to have information on an hourly basis, and that helps us very much. So let's start with TROPOMI. And TROPOMI has been launched as one of the Copernicus Sentinel spacecraft. This is here, in this case, Sentinel 5P. You see that it has a day kind of revisit time scale, but the resolution, especially for chemistry, is very, very good. This is a picture here of the spacecraft, and you see here the instrument that has been put on board. You see here the different species that are measured. I'm going to emphasize the nitrogen oxide here, but of course there are other instruments that are measured by using remote sensing techniques in different part of the electromagnetic spectrum. Well, I think this is a beautiful picture that shows you essentially an annual mean of NO2, the column, the vertically integrated column of the species in different parts of the world. And you see, of course, high values in certain areas, China, India. You see here in Europe, in particular between the UK, Holland, Germany. You see the Po Valley very well. You see what happens in the US, in the East Coast. You see Chicago, you see California, and then you see also high values in Africa, usually associated with biomass burning. You see a large industrial complex here in South Africa, and you see the cities. You see Moscow, etc. Here you see other cities. And then we can look more specifically in Europe, where we are, and you see, of course, that we start to get quite a bit of information about basically the pollution sources. Now, interestingly, you can see, if you look carefully, this is now in between Spain and North Africa. You see the ship tracks, for example. You can see also I mean, this has been, of course, a lot that received a lot of attention in the past, the amount of ozone and the total ozone that you have. You see here, for example, the ozone hole in Antarctica, I think it's in 2017, at the end of the period of the ozone hole, so the ozone hole is going away. But what is interesting is we can monitor exceptional events, like, for example, at the beginning of 2020, we had very low ozone over the Arctic. We had a real ozone hole over the Arctic, and you see how dynamic it is, and those kind of feature can be observed. Now, what satellite provides also is information about the role of biomass burning, about fires. You see the fires here, for example, here in Africa. Fires apparently, well, no, this is not the fires. This is the Chinese emission. But you see what is interesting, the fires here in Australia, and you see the plume of the Australian fires near Melbourne going all the way through the Pacific Ocean and reaching at the end South America. You see it here happening. So all that can be monitored. You can, of course, see what happened to the injection of volcano here around the Pacific that has a global effect, and all that can be monitored. You see, you can start having ideas about the emissions from biogenic species, in particular here in the rainforest of South America and Africa. And these are temperature-dependent emission. Isoprene might be the primary source, formaldehyde might be a secondary source, but you can start having some ideas about the connection between from those data on a rather global scale, the impact of the biosphere on the atmosphere. So then I moved to another approach, which is underway. It's a revolution underway. In fact, the world has decided that in addition to having satellites that look at a global scale, it's important to zoom into some regions where air pollution is important. And so the plan is to have 3 geostationary satellites that will look at those 3 different regions, which, by the way, provides a big challenge for the modeling community, which needs now to be able to get a global picture of the air pollution, but also to focus on certain region. And you see here in the back of my graph some grid, and the grid is the grid of a model that we are putting together at NCAR. It's called Musica. I'll say a word about that in a minute. That has the capability of zooming exactly where the 3 satellites will be making observations. So the Korean satellite, GEMS, is already in place. It's starting to make observations, and I can show, this is here, the GEMS satellite. Here are the species that are being measured. You can see these are the traditional species that we are measuring, but let me show you just very preliminary results from our Korean colleagues. You see on the left, for example, the ozone that is measured by GEMS, and it's compared on the right with the ozone measured by TROPOMI, and there are good connections, good relations between the two. They look very similar. But of course, the advantage of GEMS is that it will be able to give you observation on an hourly basis, while TROPOMI will give you global information. So they will be very complementary. Now, all these observations need to be put together and basically assimilated in a global model of the atmosphere. Now, the models have to deal with a large number of processes that are shown here. I'm not going to go in detail, but you see the emissions, you see the transport at different scale, you see the effect of convection, you see the transformation occurring, you see the gas phase chemistry, and also the aerosol formation and heterogeneous chemistry, all that, and then you see the deposition on the surface. So all that needs to be taken into account. So this is one example of a model at about 50 kilometer resolution that shows you at a given time the surface concentration of ozone. And you see, of course, that where the sources of NOx and VOC are important, like for example, Eastern US or China, India, etc., or California here, you see large production of ozone, especially in the summertime, and you see plumes coming out of those sources region and being kind of taken over by the dynamics of the atmosphere, which transport it in a very chaotic way. You can do the same thing with aerosols. There are now global models. This is a 10 kilometer resolution model by NASA showing the different type of particles. I think in green is what's come out of the fires. In yellow is the dust. In blue, you see the sea salt, and in white, it's the anthropogenic pollution type of particle that you see. So it's a very complex mixture. And of course, satellite provide additional information. Now, what I want to say is that model and satellite, or model and observation in general, should not be separated. They should really come together, because essentially, if we want to understand what happens, but also to predict what happens, we need to take into account satellite observation, surface measurements, and models, and assimilate them in order to have the most reliable prediction of the situation. And one example of project that is doing that is the Copernicus Atmospheric Monitoring Service that is run at ECMWF. And you can see that CAMS, here are 3 numbers that CAMS is very proud of. They're using 280 million observations every 12 hours. That's mostly from satellite. 70 space instruments, and they produce and sell 40,000 maps of information. So essentially, how does it work? Well, first of all, you have the input data, satellite observation, surface measurements, weather information, sources, emissions. All that needs to be then included in a model. And of course, here are the observations that are used by CAMS. You can see that over time, the number of satellite taken into account, the number of data has increased dramatically. Then you assimilate those data into your model. That gives you initial condition and make sure your model is not deviating too far away from reality. You get this, it gives you a forecast, and the forecast is here on the global scale. So I'm going to show you the forecast for today. And you see here the forecast for one species. This is carbon monoxide. And you see, of course, it's pretty chaotic because it's affected by dynamics, but we see what happens over China, over India, large value of carbon monoxide. We see it in Africa also, associated in Central Africa with fires. And then we see in the US, in Europe, it's more affected by air pollution, urban development. Let me show you what happens more. Let's zoom over Europe. You see, as I told you a bit earlier, from the breathometer data that were on the telephone, Northern-Italy is relatively polluted today, at least that's what the forecast says, and apparently it's the case. And France, for example, is not very polluted, but the weather is such that there is a lot of rain happening, and there was a front passing, and you see this boundary that you see here between the middle of Germany is the sign of a front that just passed in Hamburg a bit earlier today. This is nitrogen oxide, which has a smaller lifetime than CO, so it's not spread so much. It remains closer to the sources, and you see, of course, where the sources are. And we can zoom here. I took China because China has a lot of NOx at the moment in northern part of the country. And if you look at Europe, you see also a very complicated structure that shows you, of course, a lot where the emissions are taking place, and then the effect of dynamics on top of that. This is the ozone column that is predicted for today, and you can see that there is no ozone hole in the Arctic this year as we had last year. So this was a global view of the air quality, but of course we want to have more detailed information, and we want to go to regional impact. And so we take our global forecast as the boundary conditions for regional models. And of course, we take several regional models because we want to do a multi-model ensemble prediction, since models are a bit different in the way they are formulated. They're using some data that are different. And so rather than giving you, just like for the weather, giving you one single prediction, we give you an ensemble of production and a distribution of the likelihood that some events are happening. So let me show an example that we did here with European and Chinese colleagues. This is for doing a regional air quality forecast system for China. We're using 9 different models, 9 different regional models, and one, I think 8 and 1 global model. This is a project called Marco Polo Panda. And so essentially you have different forecasts. You see here forecast model number 1, and then number n, which might be 8 in this case, or 9. So we do the forecast, and then the forecasts are pre-processed, goes to a central database. In this case, it's the Dutch Met Service. We do an ensemble calculation ensemble. We calculate the median, the mean. We generate image, and then we finally put that on the web where the forecast is shown in China or in Europe. And of course, we have measurement at station that we put into, because we're going to compare hour by hour our forecast. So here's an example. You see here, this was an example for October in Beijing. The red curve here is the observation from the station, the official station in China, in Beijing. And you see the red band here is represent the variance from the different stations that are located near or in Beijing. This is the mean of the 8 or 9 models, and this is the median of them. And this is here to the right, an individual model. You see it's different from what the median is, but I show you other models. This is, so I'm not going to cite which one they are, but you can see that all the models provide relatively different daily variation of ozone here, and therefore we see that by calculating the median, we have in fact a forecast that is closer to what the observation tells us and shows us. Now, this was done by a regional model, but now the community is moving towards an approach that in fact puts together the constraint or the advantages of, let's say, a global approach and a regional approach. So the idea is to use models that are essentially have a grid that zoom in a region, but provides the value globally. And so you don't need to go from one model system to another model system. You don't need to deal with regional boundary conditions that might be uncertain. You try to do that in a single framework. And in fact, this is the idea is a new community model that will be able to provide a framework to which any chemistry, any representation of the dynamics, any physics will be able to be integrated. Well, I'm looking at my watch. I think I have 5 more minutes. And so I would like to show you a little bit, since we talk a lot about COVID-19, how the atmosphere has been reacting to COVID-19, and in particular, how satellite and models are useful to understand the response of the atmosphere. So going back to TROPOMI, this is here, NO2 in China, where of course the pandemic started and the first measures were taken in February 2020. You see here 2 years that are compared, and you see a reduction during the lockdown in 2020. If you go to Europe, you see also, basically this was a bit later in the season, this was between mid-March and mid-April, the first wave, and you see also a reduction in the pollutant. This is nitrogen oxide, which is a good picture, if you want, NO2, a good picture of the pollution. Now, if we go on the surface and we look at the surface stations, which is always good to do when you have satellite data, we see also the same kind of behavior. On the left here, you see this, the top is before the lockdown, and the bottom is during the lockdown. And so you see here the PM, the particles, pretty high level of particle before the lockdown was started, and a big reduction after the lockdown started. Same thing for NO2. You see here high value as we see in the satellite, and you see during the lockdown, everything was shut down, nothing was operating, and the level was much, much lower. But then in northern China here, this is ozone, a secondary pollutant. And yet you see is that during the lockdown period, ozone increased. It increases by almost 50%. And so if you remember this graph, this Ekman diagram that I showed you earlier, I showed you that in certain cases you reduce NOx and ozone is increasing. We have seen that operating in real through a worldwide experiment that happened during the lockdown happening. And so we tried to simulate that with the NCAR model. And so we had to estimate first, that was based also in Toulouse, the changes in the emission of a number of primary species. You see them here. This is in northern China, all going down here, except I think one of them here, it's organic compound because, well, people were staying at home, they were cooking a bit more, so there was a big increase, but otherwise you see a decrease, and NOx is here with 45% decrease. Now we look what happened in Europe. It started a bit later By the way, those wiggles are associated with the fact that there was less destruction usually, I think, during the weekend, or there was a difference in the weekend than during the week. You see what happened in North America, or at least how it was estimated, and this was estimated in South America. So we took that in a model. And so what you see here on the left is what happened in terms of the reduction in NOx in February during the Chinese period of lockdown. And you see, of course, that the NOx is decreasing here. Later on in April, when the whole world started to lock down, you can see a reduction in NOx all over the place, in Europe, in North America, even here on the western part. It was pretty dramatic in Peru and all that, South Africa, etc., etc. So now we have the models to look at that and to see if we kind of analyze things pretty well. So let's look into that. So I'm putting back the previous slides for February, and I see the reduction in NOx, or essentially in China, and nothing else at other places. Now, this is the satellite that compares for February the reduction in NOx between 2020 and 2019. So what do I see? I see the reduction in China, but unexpectedly, I see a reduction in Europe. And I see even some reduction here at the border with Canada, and I see an increase here in the southern part of the US. Well, the emission, the changes in emission is not the only cause of the change in NOx. Meteorology plays also a big role. So this one here that I showed you before assumed that it was only the emission that were changing. But if we take into account also the change in the dynamics, look what we find in the model. We see, yes, the reduction in China, but now we see also this reduction that was seen in Europe, and even a slight reduction here over the Canadian border as seen, and an increase in the lower part of the US. So the dynamics is very important. This is here what you see. These are the changes in ozone due to essentially both the COVID reduction and the dynamics. And what you can see here is that, for example, you see, for example, in Europe, you see an increase in ozone that has been here that is associated with the decrease in NOx. In fact, what was happening in northern part of Europe, you had a lot of sunshine during that period. You had a photolysis of NO2. You had more photochemical activity. You were producing ozone. And so it was not a COVID effect. It was a dynamical effect that permitted the photochemistry to work differently. So it's very difficult to do an analysis. One has to be careful when one compares 2 years, because there are other aspects that can be important. So I'm kind of done with my presentation. I'd like to finalize it by showing you one slide to tell you that all what we're doing in atmospheric chemistry today is really not isolated from a broader, more holistic Earth system approach. And in reality, this is a graph taken by a document from the US Academy of Science that shows essentially that now we need really to start developing predictive capability, starting from the sources, and they can be related to energy industry, agriculture, but also the natural processes that are evolving as a function of time. We have to do a lot of atmospheric chemistry research on emissions, transformation, oxidant formation, atmospheric dynamics, aerosol, biogeochemical cycle, deposition, and all that are coupled. This is the agenda of the atmospheric chemistry community. But we have to put it into a context where we're looking at a societal relevance and link all this with human health, climate and weather, ecosystem, because at the end, issues like security, like energy industry, environmental justice, which is becoming a very important theme, and finally, sustainable development has to be considered when we build our laboratory program, our modeling program, our prediction program. And finally, we should not forget the feedbacks on emissions. All what we're doing are going to change the emissions. And so, again, my message here is that atmospheric chemistry, as I describe it today, should not be isolated by an Earth system approach that we should deal with. Okay, so that's what I wanted to tell you. I said air is a global common. It belongs to everybody. It has to be clean, and everybody has the right to breathe clean air. And of course, space observations that the Institute is promoting so much have revolutionized our ability to monitor and forecast air quality, but finally, a very important contribution to Earth system science. So thank you very much.
Thanks very much, Guy, for this beautiful, very interesting lecture. So we have time now for some questions. So if the participants want to ask questions, please indicate this in the chat. And so we have to wait a few seconds, I think, in order the system start. So I will ask a question to you, waiting for some other questions. At the end, you said that my question is, what kind of weather dynamics is able to amplify the ozone and the nitrogen oxide patterns that you showed at the end?
What happens, of course, is that the dynamics transports a number of chemical species, and it can transport the species in regions where the amount of solar radiation is different. So it was very interesting to see that during February here in Europe, we were going to look at the impact of COVID, and we were seeing increase in ozone in the north part of Europe and a decrease in ozone in the southern part of Europe. And so we saw the same thing in China. And so in China, it was really due to the difference of pollution levels. The northern part of China is very dirty in terms of air pollution. And so it is controlled by VOC more than by NOx. So when we reduce NOx, essentially we were increasing ozone. In the southern part, it was the opposite. So we thought it was the same thing in Europe, but in fact it was not. It was just that there were no clouds in Northern Europe, and there were a lot of clouds and rain in Spain, in southern France, in Toulouse, where you are. And so the condition for chemistry to happen were different. So meteorology is a very, very important factor.
Okay, thank you very much. I think there are questions. I don't know if you see them.
Yeah, I see many of them. So
okay, so let's go.
I can read them. Okay. Will a recording be available? I don't know, to answer that question.
John Zarnecki has a question.
And said yes. Okay, thanks. Yeah, the question is, presumably the measurements from space are integration over a long line. Does it give problem of interpretation? Yes, of course. What you see is the total amount along the line. Now, this is why you have different geometric configuration for the satellite. Some satellites look from the top down, and they see the column. And the column, well, is very interesting information, but you don't know exactly at which altitude the species are. Now, in the case of nitrogen oxide, we know from other type of observation, for example, aircraft observation, balloon observation, that most of the NOx is in the boundary layer. So we can say to a certain extent, well, the NOx is essentially in the boundary layer. Of course, it can also be in the stratosphere. So all that needs to be taken into account. And we need, of course, kind of comparison or joint activities between the people who work satellite and the people who do in situ observation. This is very important. So the validation process is very important. And then sometimes you have limb observation, and so you scan in altitude much better, but again, you lose on your horizontal resolution. So yes, the answer is yes, and people are dealing with that the best they can. Ozone hole, is it decreasing or increasing? Well, first, it is essentially changing from year to year at the moment. Now, our hope, of course, is that with the reduction of the CFCs in the atmosphere, on the average, the ozone hole will become smaller and finally disappear. But it's not a linear process. It's not going to be linear in time because they are thresholds. So if you reach a threshold, maybe the ozone hole will go away a bit suddenly if you want. But the temperature is not the same every year. The threshold will be sometimes reached, sometimes not reached in the future. And so what happens is that the dynamics is making the ozone hole being different every year. This year, the Antarctic ozone hole was large, and it didn't go away for a long time because the vortex around Antarctica was very stable for a long time. In the Arctic, we normally have no ozone hole, but last year we had one because it was very cold. So there was a lot of variability happening. Let's go to the next question. Do you have an experience combining measured data from low-cost sensor, the low-cost sensor, in a fine mesh network with satellite data and modeling to increase the resolution, for example, in urban environment? Very good question. This is, this is another revolution, is the use of a large number of low-cost sensor that will be put in different parts, for example, of a city. So we're working on that already. See, there are issues, of course. The low-cost sensors are not very accurate. So you need to complement them by some other instrumentation that can validate them or evaluate how good they are doing. That's one thing. On the other thing, when you have a lot of them, if you assume that the error, which is relatively large, is relatively random, you can start statistically to see if there's coherence between what they measure, and you can use models then to assimilate what they're doing. So it is a very important new source of data, but it has to be linked with the other data that you have, in particular satellites, but also in situ observation with more expensive sensors that are more accurate and with the appropriate high resolution model. So the field is going very much in that direction at the moment, including in urban environment. Let's go to the next one.
So you have many more questions.
How accurate do you think the current estimate of PM 2.5? Well, I don't know exactly where and when. I must tell you one thing. PM 2.5 is used and very much, but I still don't know what a PM 2.5 is. Is it sulfate? Is it nitrate? Is it secondary organic aerosols? So, it's like if we were saying we have gas phase pieces and we would not distinguish between what they are. So because of the way they are measured, because of the importance of giving a single number to characterize particle air pollution, we use PM 2.5. We're using PM10 for larger particle, and we're using PM1 now more and more for very, very tiny particle that might enter in your lung much more than the others. So I don't know exactly how accurate they are, so you have to ask a specialist for that. But my only remark I had is that, I wish we would go beyond the concept of PM 2.5.
So Guy, you have still more, 11 or 12 questions.
Okay.
So go ahead.
Are there any practical application of this result regarding population health? I think that's what you meant. Yes. Well, the World Health Organization, as well as some scientists in some labs, for example, Max Planck Institute for Chemistry in Mainz here in Germany, have been trying to estimate, relatively statistically, how many people go to health problem, but also how many premature deaths you have in different countries. And of course, you never know exactly what those numbers mean, but what you see is that they mean probably that our health is affected, and that pulmonary diseases, cardiac diseases could be enhanced and are enhanced. And you see that in very, very polluted areas, there is a clear correlation between these diseases. So essentially, it's the statistical work that is done. The processes are not necessarily completely understood, but clearly, when you have an air pollution event, the hospital get full up with people with asthma, with a lot of lung problem, etc. There are a number of issues all around that, and the medical community is working on that. I think what we need is a better connection between the health community and the atmospheric community to better bring all that together. But clearly, as I said at the beginning of my talk, now people believe that air quality kills prematurely 8 million people per year. And in France, where Annie is now, it's about 50,000 people. And sometimes I ask myself, I said the following: assume that the radio would announce, or the TV would announce, that a cloud with a lot of dirt will pass over France and will kill 1,000 people. What would happen? The people would be extremely concerned, extremely nervous. And we remember Chernobyl, when the radioactive cloud came. Everybody was really afraid, didn't want to eat vegetables because of the deposition, etc. It's not very different, except that we don't have one cloud passing. We have another cloud every week. And so we're not killing 1,000 people a week. We're killing 50,000 people in a year, according to the statistics. But of course, it's not. It doesn't appear so dramatic because you don't see it. And so this is why a number of people now are saying that air quality or air pollution is a pandemic, because it's happening as, it's killing a lot of people. It's making a lot of people sick.
Okay, so yeah. You can move to the next one.
Yeah. ECMA diagram. Are there other examples? I don't know exactly what you mean, but yeah, we would need more time to understand the ECMA diagram. So I'm not going to say too much about it, but it guides you about the kind of policy measures you have to take to reduce basically the presence of ozone in particular. Okay, maybe a naive question. Or are high-resolution observation of particle and NOx accessible through Copernicus? I think yes, but I would suggest you contact me and then I can give you more information about this. Do you think some new specific satellite observation you would think can significantly improve the global estimate of PM 2.5? I'm not a specialist of PM 2.5, I'm more a specialist of ozone, but clearly, I think we need more space observation of particle, but it's difficult because of the size distribution. Okay. I'm wondering the sum of NO2, okay, OX increase, decrease during the lockdown. Good question. We looked into that. So the issue is, this is a question from a specialist. The sum of NO2 and ozone is in fact relatively constant, because what happens is that when basically, when you photolyze NO2, you reduce NO2, but it produces ozone. When you have a reactions with NO plus ozone, it produces NO2. So you reduce ozone, you increase NO2. So in reality, I need to look exactly in the model, but I think that to a large extent, and it depends a bit where in China, but I think OX was relatively conserved. But I need to go back to my model results because we looked at that specifically, but I don't remember exactly where and what. So next question, what is the biggest factor in improving observation? Improvement in detection or in computing power? Oh, I think it all depends what you really want to do. You know, if we focus on air quality, my view is that the biggest improvement should come from integrating all kind of observation into an international network and integrating the models also into that system. So I'm kind of pleading for a system by which, you know, we mimic essentially what the weather community has been doing, and we transpose that into air quality forecast and analysis. In other words, at the beginning of the 20th century, there were observations everywhere, but they were not connected. They had different quality in the data, etc. So it seems to me that we need to create a community of chemical weather forecast analysis, and that, you know, models and observations and space observations and in situ observation and field campaign, all that comes together. Oh, I'm going a bit fast because there's so many questions. How can the result of monitoring the atmosphere by satellite transport into policy that I'm at reducing pollution? There are still people ignoring the hard facts that satellite data brings us daily. Well, you know, I think we need to work on that. But I'll give you an example. I was talking about Copernicus, which is really operated from ECMWF. And so ECMWF is now putting atmospheric chemistry into a broader environmental prediction system. And that goes directly to people. And so if you turn on CNN today, every day you have air quality forecast that is coming from Copernicus. And that has a lot of satellite information, a lot of modeling information together, but of course it's transmitted to the people in a very simple way. So we need probably to show more what the satellite have been brought into that products that we are conveying to the public. So there is a lot of work to be done there. Have the changes in tropospheric model been validated by measurement? Tropospheric ozone is challenging from space. Yes, it is challenging from space because you have on top of that stratospheric ozone in much larger quantity. And so the answer is yes, there's been a lot of validation. You know, ozone is measured, the vertical ozone profile in the troposphere and the stratosphere are measured by balloon several times a week by a lot of stations in the world. I can tell you, for example, that now they have noticed that the COVID crisis have led to about a 7% reduction in tropospheric ozone, not in the boundary layer, as I showed you earlier, but in the free troposphere, above the boundary layer. So are the algorithm and code used in the modeling in open access? In many cases, yes. In other cases, no. Depends on the organization. I can tell you that, for example, at NCAR, all the models are available. So you just go, you download them, you use them the way you want. And they even have people who are telling to essentially help you to set up the model or to respond to some of your questions. How can inverse modeling improve emission data in comparison to inventory? on a city scale. I don't think we are there at the city scale yet. But of course, there is a lot of work trying to develop inverse modeling technique to basically derive or kind of constrain emission data. I think that's happening. It's a very tough way to do. It has to be complemented by inventories and compare with inventories. So it's a discussion that takes place in a group like GAIA, for example, which is used to be an IGBP group or IGAC group now. And I don't know if we are ready to go to the city scale at the moment. Okay, what is the maximum spatial resolution that we expect one day to have on satellite air monitoring? Well, we are now at about 5 kilometers. But of course, it's not so easy to get a picture of 5 kilometers. I mean, you have clouds in the way. You have a lot of difficulty in treating things. And so I believe that, we might go to 1 kilometer one day. That would be great. I don't know if this is technically feasible, but it would be, of course, super, because then we would have a lot of information about urban pollution. Okay, I can go on. You stop me when you have enough of me.
I think you have still two more questions, and maybe
okay.
After that we stop.
What do you think is the future research focus regarding ozone? I think, I guess you're talking about tropospheric ozone. Well, there are still a number of questions. There are a lot of regions, for example, where we have very little information about why we have so much ozone. I was thinking recently about one question, which was the Middle East. We have a lot of ozone over the Eastern Mediterranean, over Israel, over the Middle East, and all the way to the Gulf states. And it's desert. So why do we have so much ozone there? Is it anthropogenic? Is it not anthropogenic? Who knows? But, I think really that we know quite a bit today about ozone in the troposphere, where we have a lot of issues still. It's on the mechanism that produce or destroy ozone. In other words, other species that affect ozone. And I think my view is that organic chemistry, as I will call it, so in other words, VOC and all these complex mechanisms that lead to formation or destruction of ozone are still not very well understood. The impact of aerosol on ozone, so heterogeneous chemistry of ozone, remains also insufficiently understood. So there is a lot of deep chemical questions that are still on the agenda. Okay.
So the next one is a comment.
Okay, so I can pass it because, okay.
And maybe you go to the last question.
Thinking of future satellite sensors, what kind of new observation is missing or most needed for air quality application? Okay, if you ask me without me thinking too much, I would say send a satellite to observe air quality over Africa. Do something for Africa. Africa is highly polluted for many reasons. Biomass burning, fires, cooking, urban aspect. And so the infrastructure is relatively limited, and satellite can help very much. So it's not answering really what kind of sensors you would want, but I think if we could have a geostationary satellite that would touch Africa, that would be a great progress for understanding what happens in one of the most important continents in terms of the population.
And I would like to add that last week, we had a workshop at EC in Bern on global change in Africa. But we did not address the problem of air pollution. Many other topics, but not air pollution.
Just for the same reason as other observation for global change in Africa. I mean, Africa needs attention. Nobody's putting a lot of money to address the problem. Some do, but has to be more than what we have been doing. We cannot just work on China, India, where the pollution is high, and the Chinese and Indian groups do a very good job themselves. But I think we need to help our colleagues in Africa to develop an infrastructure to really address the problem there.
Okay, thank you very much. I think it's time to close this session. Thanks again, Guy, for this great presentation. Considering the large number of questions you had, I think the participants were very interested, and thanks again. And before closing, I would like to remind to the participants that in 2 weeks, we will have the third game changer lecture in Earth observation. It will be on sea and land ice melting, with focus on the cryosat mission, and the speaker will be Andy Shepherd from Leeds University. Thanks again, Guy, and to all of you, and see you soon.
Bye-bye.
Bye-bye.